We're talking about. This triangle represents what?
Point to the circle.
Okay, so if we draw that big circle like this, and as some of you guys realized on the last test, that this is the same as this, is the same as this, is the same as this, right? Okay? And so this theta, we're looking for this instantaneous value here, which is this part of the angle that's in the circle. However, we can also duplicate it out here on the sine wave, can't we? However, we represent the 30 degrees down here, 0 and so on, 90 degrees, and this is values in time. And of course, the entire sine wave represents this circle is stretched out in time. And if we want to do these, what are the formulas? What's the instantaneous formulas? Now obviously with what we've got here, we can use sine, right? So we've got the sine of theta equals our instantaneous, well we put a b there, so don't confuse you. So instantaneous b over b max, right? And so if we want the instantaneous value, we just flip this up, and our instantaneous is, usually write the b max first. So it's v max times the sine of theta, right? And of course, if we want theta, what is it? Sine inverse of the instantaneous over the v max, right? And of course, if we wanted to change this to current, the only difference is what? The letters change. It's the same exact thing. So we just go through here and put instantaneous over I max, instantaneous over I max times the sine of theta. So, same thing, right? Now we understand everything about a sine wave. This length is called what? One cycle. It also has a wavelength, doesn't it? And that wavelength is equal to what? Okay. And if we do it, and this is in meters and this is in hertz, right? Now if we want to make it kilohertz, or whatever, we can just cross three of these out. Now we also know that frequency is equal to what? 1 over time, and this time is in seconds. So that's all the formulas this chapter has, except for, we've already done it, a squared plus b squared equals c squared. And of course, if you want to find a, you do what? C squared minus b squared, take the square root of it. If you want to find c, you just take the square root of the other side. Alright? So now let's look at some PowerPoints here. They'll kind of take us through the chapter. WCBS is broadcast at a frequency of 880 kilohertz. So what's the formula? Now it's kilohertz, so we can use what? $880 kilohertz, right? And what do you get? What? I still don't hear you.
341.
Now remember, if I had these 3 additional zeros here, these cancel, right?
No.
The question? Okay.
So what is the 300 million again? What's that representing?
Speed of light
Speed of light.
in meters.
Okay.
786,000 miles per second. 97 meters. So what are we going to change on this? Okay.
Now we're looking for the middle one.
And we're going to bring this down, aren't we? So 297 meters. Put these back in. And that'll give me the frequency in hertz. So what do you get? What'd you get?
1,010,101.
Or
Or
1.10
kilo. 1,000 kilo?
1,010
Right?
Yeah.
So if we make this kilohertz, we can cross this out, right? Says an AC wave has a maximum value of 100 million. We'll draw it over here so we draw the whole figure. So it says it has a maximum value. The maximum value is always on the hypothesis. Okay, so it's got 100 milliamps. And it has an angle of 70 degrees. Now, if we wanted to graph this, we could say this at 90 degrees right here is what? 100 milliamps. Correct?
How did you get that?
How did I get that? Because remember that hypotenuse. Whatever this length here is the maximum value. Remember, it rotates around. That's the max value. Okay. So we want we want to find this instantaneous current at 70 degrees, right? So we're looking somewhere over here at 70 degrees. We're trying to find that value right there, aren't we? But it's the same thing as the 70 degrees in here. We're trying to find that triangle, which is this triangle here. Okay, so what's the formula? Instantaneous current is equal to what? The max value times the sine of theta, right? So we know I have 100 milliamps and 70 degrees.
The answer is 94 million.
Okay?
94.
94 milliamps. Okay, is that what everybody got? Okay, let's see if they got the same thing. Thing as it rotates around down here at 0 degrees, there's no current. And as it rotates, the current you get more and more instantaneous current till now it becomes the max. And so this little right triangle right here is this triangle here just drawn bigger.
See, I see that, but I don't get how your hypotenuse in that triangle now becomes your max on top of that.
Because this is the instantaneous value, and at 90 degrees right here, when this becomes 90 degrees, this is our max value right here. And remember, it's the same all the way through. Becomes this max value. All right? If we've got that, then it makes it easy. Now, when we go from one instantaneous value to another, we have to go to the max point because that's what they all have in common, right? All of these have the same hypotenuse. So the instantaneous values changes, but they all have the same peak. So to go from one instantaneous value to another instantaneous value, you have to go through the peak. But in this case, they didn't ask us that, and I'm bringing it up because.
And the peak will always be the phenomenon with the max.
Right, it'll always be the hypotenuse. Okay, we good on that? So this curve, or from 0 to 90 degrees, and remember, once we get there, these duplicate on the other side and down here and so on. So we only talk about this half all the time.
The other way is the same, huh?
Yeah, the others just are the
The
same.
other half is a mirror image of that side. You know,
Right.
The only difference is it's the same values, you just go negative down to the correct.
Right. And remember, the angle is here. It's just a negative value of it. Okay? So if you were here, and this was 70 degrees, and you have 30 here, so 90 plus 30, this would be 120 degrees, right? That's what. Okay. All right. An AC voltage wave has an instantaneous value of 70 volts at 30 degrees. So let's do the same thing again.
And are you always going to use sine in these instantaneous equations?
Yes.
But
Okay.
if they don't give you enough information to use sine, you have to go through and use one of the cosine and tangent and then supplement that answer for sine.
Well, we don't give you the x value because x value is irrelevant. So these are all the same. Now, it'll change once we get other things going in there, but right now. Okay, so we've got an instantaneous value of 70 volts. So I've got 70 volts right here. And it tells me this is at 30 degrees. It says find the maximum value. So if we put this in our equation right here, we've got 30 degrees. We know this is what? 70 volts. So now we're trying to find the Vmax, right?
Yes.
And so we can use what?
30.
Sine of theta equals
Range.
instantaneous over Vmax. So we just got to swap these, right? So Vmax equals instantaneous over the sine of theta. And this is 70 volts, and this is 30 degrees.
140 volts.
So this is 140 volts right up here, isn't it? Okay? And this is also 140 volts. Okay? So the next question says, now it's starting to throw things in we're going to get to. We haven't talked about capacitors, but you got to use a little common sense here. All right, it says, what does breakdown voltage mean?
When it passes, what would overcome the insulation? But I don't think that makes sense in this situation.
Okay,
In
now,
this case, it's the different force that pushes the electrons the other direction. Okay.
I've got a capacitor here with a dielectric in it. And it tells me it has a breakdown voltage of what? 125 volts? And so at 125 volts, what's happened here, if I have electrons on this side, negative ones, and then I have positive over here. What it says is at 125 volts, the electrons are going to find their way through this guy, and it actually will pop like a firecracker and ruin it. So I know one of you guys will do it one of these days just so you can prove it.
What does it say, what does it mean to be impressed?
Okay, impress means put across it. Put, so it impresses a voltage, so it's got all this force on it. It'd be just like a water balloon. Yeah. However, I had some guys who, they thought it was a capacitor. It happened to be a diode of some sort. And when they blew it up, it went up in flames instead of popping, and it created this rotten egg smell. And it went in the ventilation system. They could smell it all in the entire place. And so it smelled like natural gas.
Oh, what they call it.
And so people were trying to find out where the gas leak was at.
Were you impressed?
Yeah, I was impressed. Because I went home on around there, you know, us, we don't know nothing about it. Well, it smells really bad down here. We don't have any gas down here.
I don't smell it from
Yeah, so anyway. So answering this question, can this wave be impressed across the capacitor whose breakdown voltage is 125 volts?
Too high, right?
It's too high. So that's why when we get to this stuff, when we look at these peak values, even though we're down here running at 120 volts, we still have to look at that peak value. It's up close to 170 to see if our equipment will work with it. So in this case, it won't work, will it? Okay, so it says an AC voltage has a maximum value of 155 volts. Find the phase angle at which the instantaneous voltage is 110. We'll probably do this one here. You've probably seen it before. So if we draw our triangle, trying to find theta as a maximum of 155 volts and an instantaneous of 110 volts. We all know what that looks like in a circle and a sine wave, right? So theta is equal to what? 155 volts times the, actually we need to write it the other way, right? Cosine, the sine inverse of 110 divided by 155 volts, right? So 45 degrees.
And that's the phase angle?
Yeah. Now do we introduce another term? Phase angle is still the same.
Theta, that theta is the phase angle.
Right, that's the same one in the sine degree. Now, what does that mean? And let me draw it a little to emphasize it. So it means at this point, this is the effective value, isn't it? And remember, that's equal to 110 volts DC. Effective means it does the same amount of work. Yes?
So the effective value is at 45?
Yeah. Remember, we said what? RMS is equal to what? 0.707, which is equal to what? What's the sine of 45 degrees? 0.707. So if you actually draw that in our little circle here, 45 degrees means what? It's halfway through, isn't it? So we have our 45 degrees here. That means this side is the same length as that side. And so they've designated that as our 45, but it does equal the same power that a DC circuit would create at 110 volts. We have to put how much in? 155 volts, but then we say it's 110 volts. So if you got 110 volts at the house, its effective value is same as 110 volts DC. However, you got to put 155 peak in to get that value.
So the only time we're going to be using that RMS, the .707, for when we're finding the effective value of AC in comparison to DC.
No, every time you read your meter, it reads RMS.
So this is what your meter reads, is RMS. And so every time you get that meter out and read something, it's reading an RMS value. And so what?
Oh, so you're saying to reach that value, you're going to have to put more volts.
Correct.
Than really what's being displayed.
Right.
I think, would you be able to measure your peak? An oscilloscope?
Yeah, you'd have to have an oscilloscope. Now, the reason we want to know RMS is you may have something that says 90 volts RMS. So it has an effective value of what? 90 volts DC. And you're going, okay, but you really need what? 110, and so your equipment's got to work harder because it's got to increase more amperage in it to be able to do the same amount of work. And so that's when things start burning up. Or you may have a problem where it's showing this. And this makes this guy way up here, doesn't it, the peak? And then that's when you start burning up insulation, not because it's hot, but because the voltage is traveling through it. It can short out. All right? So we want to understand what we're actually reading with our meter. RMS, that's a very important value for us. So theta is 0.707 or 45 degrees. We compare AC to DC. And what does effective mean? If I put 120 volts in there, we know that's what? The effective value of our AC, right? So it means when I figure this out and I put in 10 amps, I'm getting how much power? 1200 watts, okay? So we know we're getting this much work out of it, then we could convert it to horsepower if we wanted. And we could say, okay, we're creating this much energy. Now remember, when we graph DC, remember, it jumps up almost instantaneously, doesn't it? And then we get all of this area right here is our power, our watts being done, isn't it? If we do the same thing with the sine wave, and this is my 120 volts, then of course I have to have what? 45 degrees, don't I? So I have to get my RMS value, but I have to put this much into it, which is what, almost 170 volts, to get 120 out of it. And so this area now under the graph is going to equal this, but it's not directly straight across as I've drawn it. It's a little higher up here for me to get the same effective value as 120 volts DC.
Okay, it's because it's oscillating so fast.
Because it's oscillating so fast, yes. So let's look at this. An AC wave has an effective value of 110 volts. Well, you can answer this one like we just did.
55.5.
Okay, and the instantaneous value at 40 is what? Well, I just reversed and stuck the little values in a little differently, so I have to draw it out. Right triangle, 45 degrees,
Isn't it 40?
110 volts.
It's 40 degrees, not 45.
Oh, excuse me. That's a big degree sign too. That's better. Okay, so what is the maximum value? See, find effective, say the AC.
Wouldn't your effective be the
Yeah.
110?
Yeah, this is my 110.
I was confused.
Yeah, I confused a bunch of people, including myself. Okay, now we want to find the max value here. Okay. So what formula are we going to use?
It's by 10%.
Say again?
110 over sine 40 degrees.
Isn't it 171?
That's your answer.
Is that what we write? Is that correct? Well, if you don't remember, it's what? Sine of theta equals the instantaneous value over the V max, right? And we have this value, and we have this value, so this comes under, right? So that's correct, isn't it? So what do we get?
171.
171 volts. Didn't we? Now this is where you're going to get caught on a test if you don't pay attention. Okay, so to get to the max, we have to say this effective value is what? Has effective value of 110. This angle is 45 because we know that's what the effective value is, isn't it? And now we've got to get to the V max. So what's our formula going to be?
Max equals 110 over sine 45.
Or we can multiply this by 1.414, right?
And those 110 or 40 degrees only?
Well, what he's telling you is they're giving you this 110, this is effective. Effective is what, 45 degrees? Don't get confused with that being there. Or you can divide this by 0.707. These are the same, right? Does everybody see that? You see that, Candace? Okay.
So, yeah, okay, so that's 0.707 is at 45 degrees.
Yes. That's the
And
sine
then
of
divided
45.
two is at 90.
But if you take it from the bottom to the top, it now becomes 1.414.
That's your max.
But what is that?
What is that?
Like, what does that represent?
RMS, or effective value.
And so that's the 45 degrees.
Remember, go back to this circle again. If this is what? 45 degrees, at this point, this side's the same as that side.
Yeah.
Okay? And so we say this is our RMS value, our effective value on a sine wave.
But are you also saying then?
It's
your-
only on a sine wave
Your angle is always gonna be 45?
for RMS,
When we
yes.
talk about effective value.
RMS.
Yeah, ineffective value. Remember, RMS effective is 45 degrees or 0.707 up.
Okay, but I guess what I'm asking is whenever we see that on a test and it gives us the effective value, we automatically have to assume
That's at 45
that
degrees.
it's 45 degrees.
Yes.
And if it asks us to solve it at a different degree than that, we have to go back through
Peak.
and solve.
Yes.
So the first step is always to go to your max value.
No.
You put it as like the instantaneous value, right?
Yes,
Unless they give you the max, then you have.
Once it gives you a number, you automatically know that's what's the continuous value.
Correct.
You can just.
right. Anytime we give you, unless they tell you it's peak, it'll be an instantaneous value.
So then, if you want to find the peak, you're basically taking the 110 and multiplying that by 1.414.
Right. Which is the same as dividing it by the sine of 45 or 0.707. Because if you take 0.707 and do 1 over it, that gives you 1.414.
So if I just divide 110 by 1.7.
Does everybody see that? Let's back up a second. What's the sine of 45?
0.707.
0.707, okay? What's 1 over 0.707, which is this right here? 1.414, okay?
So what does sine equal?
Sine's a value.
What is that?
It's a ratio of the sides of the hypotenuse.
Oh, so sine, cosine, tangent are just
They're
ratios?
just ratios of the sides. Okay? All right, so if we do that, what do we get here for the peak?
155.
So 1.414 times 110, or divide it by 0.707, what do we get? 155.5. Okay. Now, if we take that value and put it right here, now we're going back to 40 degrees. Now we're going to change this formula to what? To 40 degrees and 155 volts right here. Now we're trying to find this instantaneous value here, right? Okay, so what's our formula? Is that correct? No, it's messed up, isn't it? So what's it going to be?
So you got.
Sine of theta equals what? The instantaneous value over V max, and I have 155 volts here, and I have 40 degrees here. So does that work?
Yeah.
Okay, so it does work. So if you have a question, go back to the formula. So what does the value come out to be?
99.6. But he was right, we were wrong. I got 100. I got 100 volts.
29.95.
Yeah, it depends on how you round off. So it's going to be 100 volts, right around 100 volts. Now, we're not going to do this quiz. What do we use an oscilloscope for? This is the beginning of an oscilloscope. An oscilloscope is a device we use to measure peak and frequency. And so an oscilloscope has graduals. It's kind of like hairs on a scope, except they take these all the way through. And so on. Okay, some of them got them drawn in, but the whole screen is divided up into squares. And then what it'll give us is find the frequency of a signal whose period is 4 seconds. So frequency is equal to what? 1 over time, which is 4 seconds. Hertz, right? Okay. And everybody recognize that 1/4 is the same as 0.25. Okay, here's another one. It says an AC wave shows a peak of 3 divisions. And it's 5 volts per visit. And how wide is it?
5 volts per division.
Okay. So we got something that comes through like this. We'll put this at the 3rd division. And each one of these divisions is worth how much? 5 volts. So how much voltage is this peak worth?
15.
So you got 5, 10, 15, right? So if you got 3 divisions of 5 volts, just multiply them out. Fairly simple. However, if you've never used an oscilloscope, yeah, go ask Paul. In fact, tomorrow I'll ask Paul to show you the oscilloscope. If you're confused on oscilloscope, have him pull one out and show you how they actually work. So here's one with an AC wave. This is a time based of 10 divisions set at 1 millisecond per division. So we're doing an entire wave, aren't we? So 1, 2, 3, 4. So if we snuck one more in here, so this is 5. And then there'd be 5 more out here when this came up. So it'd have 10 divisions at what?
1 millisecond.
At 1 millisecond per division. So you multiply those together, and what do you get? You're going to get 10 milliseconds, right? It's that simple. Okay, what is the frequency going to be?
100?
So you got 10 milliseconds. So you got to go 1, 2, 3, right? So 0.01 seconds. So what did you say? 100 hertz. Does everybody know what a vector is? What is a vector? Anybody know?
Value with the direction.
Action and
Magnitude.
magnitude.
Okay. So I have an electric iron that operates from 110 volts. You know that 110 volts is effective, right? Draw 60 hertz in the line. It says draw a phasor diagram, find the current and the power used by the iron. So how much current? How do we find current? What's Ohm's law? Remember, this is chapter 1. So what's the formula? Okay. And my power is what?
Voltage times amp. So it'll be 1 times
Volts
5.
times amps, which gives me 110 volts times 5 amps.
So 150.
550 watts, okay? Now, how are we going to draw a diagram of this? Now remember, we talked about resistance. Resistance, voltage, and amperage are what? They're in phase, aren't they? So if this is my voltage diagram, and this is my 110 volts, my current would look like this, and it mirrors it. This would be my 5 amps, right? Now if I'm to draw a diagram to represent the power, I'd have a diagram like this representing 5 amps, and since they're in phase, this would be my 110 volts. And this whole line would represent what?
Power.
The power. Okay? So they're in phase. And so this whole thing right here would equal my 550 watts.
So how would that be in that? In your wave? How would that power look like?
Power is the combination of these two.
So I'm saying, would it be like
Yeah.
huge down and?
Yeah, so these are put together. So actually this would be what? Well, this would be my watts.
And then resistance? How would you draw resistance?
I don't draw resistance. I'm just drawing the current through the resistance. And what we said was, this is a resistor, right?
Oh, so that wavelength is the wavelength.
So this represents what happens in this resistor. Okay? The resistor is just a device we put current and voltage through. So we can't do anything with it.
And that's a phasor diagram.
This is a phasor diagram.
That's a phasor.
Okay? Phasors, that's the arrows. Okay, and remember, current and voltage are in phase through a resistor. Okay, you got that ingrained in your mind, you got to know that the rest of the semester. All right?
One more time here, please.
Current and voltage are in phase through a resistor. Okay, they go in the same direction, X direction.